Hi folks, Titus Murray here, Southern Highlands Structural Geology. Today I'm actually in Canberra, where we're having a look at an amazing outcrop right underneath the Houses of Parliament here. It's a folded and faulted Silurian section, some amazing syndepositional faulting in here. And it's literally been preserved as they were building our Parliament House. So you can see it sits between the two Parliament Houses, the old and then the new Parliament House, which is one of the few parliaments you can actually walk on top of. Anyway, today we're going to be talking about groundwater faults. It's going to be thinking about how we can characterize faults, how we can conceptualize them, and then how we can model them, just as a primer to think about faulting and hydrogeology.
Hi folks, so we're back having a look at faults and hydrogeology. So this is a bit of an introduction to training that we've put together, and it's based on the last 3 or 4 years. Really, we're thinking about taking the oil and gas ideas we've had and bringing them into thinking about fault zone hydrogeology. So the work's been done. A lot of this work's been developed with Bill Power from Power Geoscience. He's a really good geomechanic and structural geologist over in Perth in Western Australia, and a lot of the ideas have come about from spending time in the Southern Highlands. The photograph here is actually from Wayne Nah from the US, his practice is mainly on fractures, but this is the Blue Mountains, so very close to us, same geology, very similar geology, and this is what I've been sitting there thinking about on a regular basis. Faulting and groundwater is a big deal here in Australia, partly because we've got a lot of underground coal developments and other mining, but predominantly coal and coal seam gas developments, and it's something that's thought about a lot by people, often lay people, who have the sense of faults being a visceral connection to the subsurface, to the surface, and to their aquifers and the groundwater-dependent ecosystems, environmental systems that they love. Here's a great cross-section from the Newcastle Herald. This is a local newspaper in the city north of Sydney, and it's describing the Gloucester Basin and the coal seam gas developments that were being proposed for there. And you see they've done a really good job of just putting together a nice cross-section. It describes the fill in the basin. You've got an idea about where the coal seams are, really good faults, where the surface aquifers are. These are the farmers' bores and groundwater-dependent ecosystems. So this is how Joe Average, the average farmer, the average person who's concerned about the environment, is thinking about faults, is how these faults connect to the surface. And what we've been trying to do is think about how, as scientists, we can better describe these processes and systems. Fault seal analysis has been a big part of oil and gas geology for the last 25, 30 years. We've thought a lot about the processes. There's been a lot of study spent on it. But in general, it's all been about how faults seal or how faults leak. And this really nice work from Skivik et al. Really gives an idea about where we're thinking about and where we're anchoring our ideas. In structural geology, there's a tendency to see faults as barriers, whereas in hydrocarbon reservoirs, and hydrocarbon reservoirs. Whereas in tunneling, there's a strong sense that faults are flow units. And there's a really good reason for that. If you're tunneling into a fault, your concern is not about its sealing, but your concern is about flow up and down the fault, dropping water into the tunnel. So that's your big concern. In hydrogeology, there's also a sense of faults acting as conduits, and less so the barriers. But this mixed modal approach of, well, is it a low perm core and a fracture transmissive damage zone, is a nuanced approach to it all. So the most important thing to recognize by a fault is a displacement feature. It's not a line on a map. It's not a permeability feature. A fault strictly is displacement, and you have to demonstrate you've got displacement. Not just sit there and say it's got displacement. You need to demonstrate what the displacement is. The guys from the fault analysis group have done a fantastic job of putting together models of how faults displace, how displacement works along the strike of the fault. And so there's this really nice model. It's come from a bunch of outcrop studies, but it's widely used, of having a central maximum displacement in the fault and diminishing to the tips. Now, there's more in the background to fault seal theory and how fault risk works in these slides that I go through this approach. But fundamentally, that's the upthrown side of the fault. That's the downthrown side of the fault. We've got our central maximum displacement, and the displacement diminishes out to the tip or out to the edge of the fault. So that's the upthrown side, that's the downthrown side. So in geologic terms, that's the footwall, and this is the hanging wall. If you look at the difference between them, you end up with this throw profile. And the throw profile should be a systematic displacement profile. Fault Analysis Group and various other people have described this, but they didn't invent it. This is actually material science. This is how this is how materials break, and faults are just the same as concrete, as any other material. It's just material science about how things displace. If you've got multiple faults coalescing, so often you'll have two faults. As they grow, they see each other, they coalesce. There's often a relay ramp or a zone of not quite overlap, and you'll end up with these multiple displacement profiles set in there. So this is one of the tools that we can use to show and demonstrate that we've got a sensible displacement. The other bit of work that I really like thinking about is the length and throw. So this is the work of Schultz and Fossen. It's well worth getting Fossen's textbook and having a look through it. And the idea of this is that we have the increasing length of the fault, and as the fault increases, we have increasing displacement. This is a log-log plot, and we end up with depending on the basin, we end up with a relationship between length and throw that we can use to go and check the validity of the faults. This fault here is abnormally long for its throw. So we can use that to check it. The other thing that we can look at are distributions of dip. Faults should be dipping at a sensible dip range. The mechanics of faulting means it's very hard to have extensional normal faults dipping at low angles. Your faults are going to form as conjugates. Sigma 1 is vertical. You're going to have conjugates around that, and you're going to have conjugates, meaning this fault will dip at 60, 65 degrees, somewhere in that range. Now, if the whole system's been rotated, then you can end up with one steep and one shallow, but your conjugates should show you that. So the dip is another important one. So before we start to think about the hydrogeology, we need to show we've got a valid fault in the first place. So there's a range of different models for how fault zones, to think about fault zones, and we're going to go through a number of the published ones about hydrogeology, and we'll come round to how we perceive it, having done a whole bunch of field work and work in the oil and gas and rad waste industry. There are two papers that are commonly quoted by people in groundwater. There's Kane et al. 1996 and Victor Benz's paper 2013. And what they propose is that you have fault zones that are a characteristic for a fault. You have a fault which has a wide damage zone, or you have a fault that has a low core, and so there's this idea of a core and a damage zone, and you sit there in some sort of matrix between having a wide damage zone and a small core, having a wide core and a low damage zone, having a wide core and a wide damage zone, and it suggests these as types of faults. These are the types of faults. Bentz then goes through and says, well, look, we've got different rock types, and we're going to get different types of faulting in relation to rock types. In both of these papers, there's actually very little for us to work with in terms of, well, there's no actually maps of displacement. We don't understand what the displacement is. And there isn't a lot of work being done or demonstrated on the fault zones themselves. And this is in contrast to a lot of the oil and gas literature, where there's extensive amounts of work published and shown in the paper. So when we think about faults, they're not strictly I don't feel as though we've got a situation where we have a fault that comes out of the box and it's, I'm a thin core and wide damage zone, or because I'm in a limestone, I'm going to be hit like this, or if I'm in a clastic, I'm going to be like this, or if I'm in a fractured granite, I'm going to be like this. So here's a nice fault. This is from Picton, very close to me, top of the Hawkesbury Sandstone. This is a cutting under a railway, and this stuff's actually published out on Gigapan. So if you want to have a look at it, you can zoom in and have a look at this thing. So the way we talk about geology and faulting, we have a footwall, which is the upthrown side. This is the hangwall, downthrown side. That's my meter rule, and that's about 1.5 meters there. So the red thing is my fault. And I've marked in some layers in the hang wall have been dropped down in my normal fault, and I've got my layers in my footwall here. Strictly what happens is the hang wall drops down, the footwall stays stationary. So that's how we'd see it as a geologist. As a geologist, we're all about, where's the geometry? What's happened with the topology of that? Now, if we start thinking about this in terms of flow features, and this is where a lot of my practice in terms of the oil and gas work has come from, and increasingly groundwater, is we're breaking this up to understand how the fault segments or interacts with aquitards and aquifers. So the whole idea is, how does this fault change the dynamics or the connection to my semi-confined aquifer? So now what I've done is I've marked in my aquifers on the same fault. I've marked in where my fractures are. I've also annotated where I've got fault rock. So what I've done in here is I've described the static structural features that will go into thinking about flow. So these would then be my aquifers between my aquitards. I've got fractures, and that's my base starting point. Now, to conceptualize the flow and start to talk to modelers about how we'd get flow around this, we then come to this static conceptual flow model. And in this, what we've got ourselves is we've got we've described in here in these areas, we're going to be seeing matrix flow. We're going to see matrix flow in and out of the page. We may have a different permeability vertically to horizontally, but still we can have a matrix dominated system. In here, we're juxtaposing against an aquitard, and we may get some water through across there, but it'll be dramatically reduced, not because of the fault, but simply because of the topology, simply the connection. I've connected an aquifer against an aquitard. These fractures then have fracture transmissivity, so they've got flow within the fractures, and that flow is a different bit of physics to the matrix. And we're going to start to see flow in and out of the page. So we're going to see the flow in and out of the page with the fractures. We've reduced the flow against the fault, and we've got some areas where we're going to slowly get flow through the fault rock. But in here, even though the fault is the most dominant thing, when you start to say imbalance, well, these fractures are probably the most important thing in terms of the flow. And so this would be our static conceptual flow model. So one of the key tools that we use to try and understand how to describe faults, and as I said, they are displacement features, is to look at the displacement in something called an Allen map. And what this is it's a geometric tool that we can use to understand what's on both sides of the faults and start to understand to recognize it. What the connections are. It was put together, it's been used for a long time. It's often called a fault plane profile. But Allen in 1989 put together a beautiful paper that describes the process of how migration of hydrocarbons works through faults. And one of the key things he says is, well, faults are neither a seal or a conduit. They are a patchwork of connection, and understanding where the hydrocarbons are migrated and then being entrapped is reliant on understanding that connectivity. It's a really good paper. It's well worth having a read. It should be noted that everything he did was done with pencil and paper. This is not, it is easier in some cases to use a modeling package, but you can do all these things in pencil and paper. So the idea is you have two aquifers. You've got an A aquifer and a B aquifer. A in the footwall, and that's on the other side of the fault, and B on the other side of the fault. And then what we're going to see is the fault plane that we're looking at is down juxtaposed across here. So this is then the A in the hang wall, A in the footwall. So A in the hang wall on this side and the footwall on the other side. Again, B on the other side, B on this side. And what we're looking at as these zones of overlap or these juxtaposition windows. So I'll put a nice little pattern for these so we've got ourselves an idea about where flow can happen. And that's where A in the footwall, A in the hang wall is juxtaposed against B in the hang in the footwall. So it's A in the hang wall juxtaposed against B in the footwall. And this is where, for instance, if I had a flood event, this aquifer filled, it then would allow us to recharge the B aquifer through these juxtaposition windows. And again, all of this stuff can be done on pencil and paper or in Excel spreadsheets. We've written software to allow to do it probabilistically, but the whole idea is you can do this by pencil and paper. And what you're doing in here is just producing a whole set of cross-sections. Yes, you can produce cross-section, but you're going to have to produce a cross-section at incredibly fine details to try and understand this area. And you will get an idea about where they're juxtaposed, but you won't get an idea of the geometry of this juxtaposition. One of the things you'll find as structural geologists and coming from the structural side of things is that we're driven by the geometry. That's what describes the displacement, describes the geometries. And that really informs how we can think and talk about the flow. So a lot of people in hydrogeology think about fault zones, and the papers are all about fault zones. A lot of the stuff in the oil and gas literature is actually about fault geometry. And so you can see we've got this overlap. We've got, different people talking about similar things, but using different bases to them. So let's have a think about the fault zones. So what we're thinking about here is that we've got ourselves a volume of rock that we're going to look at. So Victor Bentz has put a paper about fault zones, and look, there are some problems here that we need to really get our heads around. He suggests this is the approximate range for a fault core. Now we've got the anatomy of the fault, we'll see is the core and the damage zone. And these are, and then describing the different techniques you can use to interact with this in terms of the structural geology and the hydrogeology investigation of this core. The problem with this is that it suggests that the fault cores are too wide. If you take here's a proximate zone here and put it on Susanna Sperovic's work, this is the Equinor Statoil Hydro's database of fault core and from a range of different areas. And you can see that Bentz's fault core width is very wide. Similarly, if you compare that to Conrad Child's work from the fault analysis group, we're very much on the upper side of fault rock thicknesses. These fault rocks are down in this area in here, not up in here, and that I think is a part of why in hydrogeology we think of fault zones. What's important, these anatomy of these things, it's important, it's useful. This is a picture of, again, this is up on Gigapan. This is the Miri outcrop in Sarawak, north coast of Borneo. And you see we've got ourselves what looks like a really good thick fault rock in here. We've got ourselves a damage zone. And these conceptual models have been put together about having a fault core with sliding surfaces and this increasing area of damage around the outside of it. It's important to remember the scale of these things. So that looks pretty good. Well, that's actually a 70 meter displacement, 60, 70 meter displacement fault. As you'll see in a little bit, there's a really nice paper that Silvia De Rosa has put together that describes this fault rock and looks at the uncertainty. But, this is a big fault. And when you think about it, your 50 meter throw fault might have itself a 20 meter damage zone. Now that's pretty thick, and it might have a 0.5 meter fault core, and that's really thick. So that gives me this aspect ratio of 2,500 to about 5 kilometers, and that gives me an aspect ratio of 0.02. And what I've done to use that, as I said, 50 meter throw fault, I've used Schultz and Fosson's plot. I can then say this is what my length is. 50 meter ends up here. There's a set of relationship that Conrad Child's put together that I can say, well, what's my displacement thickness? So we can estimate these values reasonably well. What's important to think about this, though, is that if I get an A4 piece of paper, and here's my telephone bill, my telephone bill is about 0.5 millimeters thick. It has a maximum length of 300 millimeters, and that gives me a ratio of 0.02. So this piece of paper, I don't think it was a three-dimensional object. This looks like a three-dimensional object, but you have to remember, in terms of what we're thinking about, that's my fault zone. So we're talking about a fault zone that is really very, very thin. And these are using, I've over-egged, I've over-pushed the numbers on this. If you have a look at Sylvia's work, this is the photograph we were just looking at just down in here. This model's up on the internet as a 3D model for you to have a look at. It's not the best of resolution, but it's still up there. And Sylvia's put this paper together looking at the variability along strike, taking scan lines at meter intervals, looking at how thick the fault rock is. So this one's got a nice three-dimensional exposure. All of this is a nice three-dimensional exposure. And in along here, she's taken these a length, looked at each meter, looking at how thick is the fault rock, how wide is the damage zone, what's the nature of the material. Now, the idea we were doing this for was to have a look at some of the algorithms for predicting fault rock thickness. So the idea is if you move 1 meter to the left, you should have the same throw and you should have the same stratigraphy. You move 1 meter to the right, you've got the same stratigraphy and throw. Similarly, if you go 2 meters, so using this and using the variability, she was able to produce a variogram. And from the variogram, it's looking at the difference, effectively the variance between two sets of points, all these sets of points, so that if you move 1 meter left or right, you're pretty similar. If you move 2 meters, you're starting to get quite dissimilar. If you move 3 meters to the left or right, you're incredibly dissimilar. So these things are very heterogeneous. Also, it's important to note that about every 5 meters, there were faults in the whole fault rock. So there was a total absence of fault rock. So there we've got ourselves thick fault rock, but as far as the fluids are concerned, it's how thin it is, not how thick it is, that matters. So effectively what we're saying here is, here's my fault zone. Well, try and do this away from the speaker, the microphone. This is my fault zone now, because I've got myself a set of holes all through this. And in terms of the hydraulics of this, those holes are actually more important than how thick it is and the geometry of those holes. And we'll come to area in a little bit. So how do we know about fault flow? Well, a lot of my work has been about looking at hydrocarbons being trapped for long periods of time. I've got a whole bunch of case studies in the oil and gas section. We'll go through this. In particular, this Corallino one, where we can predict the fluid contact to a high degree of accuracy, and it's all about getting the estimate of where this Chuka Shoals thief zone is. And so what we've done a lot of work on is understanding why we've got hydrocarbons trapped. The important thing to recognize the difference between a reservoir and an aquifer. A reservoir has oil in it. Now, as soon as I get to oil or gas, as soon as I get to that red line there, which is my oil water contact, all of this is aquifer and all of this is reservoir. There's nothing actually very different. And the difference between a seal and an aquifer and an aquitard is not that great in reality. In general, we see our seals acting as pressure boundaries for aquifers. So if it's acting as a pressure boundary, if it's giving us a difference in head for our aquifers, then it's going to be an aquitard. A seal strictly is something which has a capillary entry effect for oil. So we've got a seal here over the top of the oil field. As we get down to here, that seal magically becomes an aquitard. Yeah. Semantics. The whole idea about this study, and again, this is all published out there and you can have a look at it, is that we can predict the oil water contact with a high degree of accuracy because this Chuka Shoals juxtaposes against our main J0 aquifer, which suddenly becomes the J0 reservoir up here, and we get a small error. We haven't just done this for a small number of cases, we've done this for a large number of cases. And in general, we show that these fault juxtapositions are controlled not by any fault rock property, but instead they're actually controlled by the geometry. So the geometry is the really key aspect to this. Language of flow. So it's important when we're talking and thinking about things to try and use the right language. It really helps discriminate thinking and helps you come up with the right sorts of models. So we're going to start to think about the matrix and fracture flow in and around faults. So one of the important things is to sit there and think about is, well, look, Darcy flow is really different from fracture flow. There's a strong tendency to talk about dual porosity, dual permeability systems, so fracture porosity, fracture permeability. But I find it's actually really good to start using the different terms, talking about fracture transmissivity, for flow through fractures, and fracture storativity for the storage within the fractures. And these things are often very, very different. The physics of them are very different. If you look at the Darcy flow equation, it's all about the area and thickness and this permeability term that drive the whole flow. Whereas fractures, it's all about the aperture and fracture height. And it's much more like what's the diameter of the pipe that I can move my flow through. And obviously with fractures, I'm going to have asperities that are going to minimize, reduce the flow. But fundamentally, it's about this cross-sectional area. This term here, effectively, aperture and fracture height give me like an area. And what's missing out is this thickness permeability term. Now, we get fracture flow within porous rocks. So this is Hawkesbury sandstone. It's not fantastic porosity and permeability, but it's still there. And you can see these hydrothermal fluids have moved through this in around dikes, and they're preferentially moving through the fractures rather than moving through the matrix. When they get to the fracture, they then go into the matrix. And these separations in flow are really important. What happens with this is as we get close to the damage zone, we're going to see more fractures, and this flow is going to be preferentially parallel to the fault. So it's going to be parallel to the strike or parallel to the surface of the fault. And if we think about fractures in terms of aquifers and aquitards, in general, the aquifers are going to be porous rocks. They're going to be more firm. They're going to be stiffer, and they're going to have fractures all set in there. And this is something called mechanical stratigraphy. So I've got aquifer, aquitard, aquifer, aquitard. I've got a stack of aquifers and aquitards here. In oil and gas, we refer to this as stacked pay or stacked reservoirs. But what's happening in here is that my flow is going to be parallel to, it's going to run in and out of the page through these fractures. And you can see these fractures don't propagate up over through the aquitards. These aquitards, because they're ductile, because they're and they actually have reasonable porosity in them, but they've got very poor permeability. The fractures, the surface, the grains can rearrange, and they can accommodate strain without fracturing. So you can see a feature in here is skipping up through the system, breaking the aquifers, but not the aquitards. And it's important, and what we're saying here is these fractures are going to form orthogonal to the bed bounding surfaces in general. And they're going to form due to the weakness and strong rocks, giving us a mechanical contrast. And the whole idea that we have got self-healing. So even if the fracture does propagate into the aquitard, because it's a finer grained rock, it will start to self-heal. And so we talk about this. This is an example from Wayne Na, where he's taken some of the narrowbeam group, and you can see how we've got a set of these fractures in this main sandstone, and they generally terminate on this shale layer. And this is, you actually walk around through these are the Blue Mountains, and see many of these fractures terminating on the shale layer. Every so often you'll have a through-going feature that goes through, but those are far more widely spaced than the ones that are bed bounded. And you can see here, as opposed to my previous example, I had thick aquitards and thick compared to my aquifers. Here I've got a very thin aquitard between these two big sand bodies. You can see down in here my spacing of my fractures is even denser as I get narrow, as my bed height gets smaller. As you can see, even though we think about permeability a fair bit, what I've been stressing is this fracture transmissivity, or the in and around the damage zone, and the geometry. And I come back to the thing that we really can work out generally is the geometry. If you think back to Bentz's diagram, we've got all these geophysical methods that give us some idea about the geometry, and we've got a bunch of geological methods that give us that larger scale. But there are very few methods that actually allow us to see the permeability, and there are very few methods, even fewer methods, that allow us to understand the fracture flow characteristics. Maybe some of the production logging, but it's a really small number of tools. And so this is some work that Geoscience Australia did on the Broken Hill Managed Aquifer, where they've used airborne electromagnetics to better understand how near tectonic faults influence groundwater recharge for a aquifer recharge project. The key bit to this is that this area in and around Menindee there's a quaternary layer, and the key thing is this Blanchetown clay. This Blanchetown clay is a massive lake. It's Lake Bungunya, deposited in Lake Bungunya, which is one of the largest ever recorded freshwater lakes when the Murray River was dammed up. And so we've got ourselves a quaternary layer from the Murray-Darling system. We've got this big clay deposit from a lake, and sitting underneath it, we've got actually marine sands, which are really nice, clean sands. And so how do you get floodwaters filling the quaternary to refill down through into the Calaveral through this Blanchetown clay? Go and have a look at McLaren's work. It gives a really nice idea about how big this lake is. It's a great story. So from the airborne AEM, airborne electromagnetics, its helicopter flies up and down over this with a source, with an electric source and a coil to receive. We can start to see where the Blanchetown clay is, and we can see the difference in the surface aquifer and the deeper aquifer. Ken Laurie and his team went through and picked all the faults, picked a whole bunch of faults in the AEM, produced these fault maps, marked up how much displacement they had on them, looked at the windows of juxtaposition and started to rank them in terms of windows and size. And so we've got a range of faults through here which have a length and have a throw. Oh, we can now start to use, these are large faults from crustal faults from outcrop mapping, but they sit in a sensible range. And what we've also done is there was debate about, well, were these monoclines, were these actually folds rather than faults? And if you've got folds, then you wouldn't have a juxtaposition windows. And so what we've done out here is we've plotted out a set of monoclines from the Sydney Basin to show how these have got a relatively long length for their fold displacement. And they sit outside of the fault range that the guys at GA picked. So these look like faults. So what we've done then is produced a set of Allen maps, stochastic Allen maps. You can go back and have a look at the video I've got about how fault risk works. What we've done is we've used fault risk to do a stochastic Allen map. So we've put a range of thicknesses, we've put a range of V-shales, and then we've used Susanna Sperovic's equation for fault rock thickness and permeability to give us an idea about how much fault rock we're going to see, given it a delta P and a viscosity, and that allows us to calculate a Darcy flow for that juxtaposition window. So from that, we then get each of our faults, the quaternary, we get a table that says, well, hey, when the quaternary touches the quaternary, 100% chance of this happening, its area is going to be 46,000 square meters. Now, that's a big number. And the standard deviation is 14,000. So these are big numbers. These are big areas we're seeing. 27,000 square meters, 34,000 square meters. These are really big areas of juxtaposition. The juxtaposition we're interested in is this Calaveral versus quaternary, because it's the quaternary on the downthrown side, allowing floodwaters to let the water run into the Calaveral underneath. And so it's these ones in bold that we're actually interested in. And see, they're smaller sizes. So the quaternary juxtaposition is 46,000 square meters, whereas the one that we're interested in is an order of magnitude smaller. And then you can see the Calaveral is 54,000 square meters. So these windows it's important to know about them. Also, you can see that these windows aren't always there. For this fault here, there's only 75% chance of having a window. So there's a probability that the displacement, there's an uncertainty about the displacement, there's uncertainty on the thickness, and uncertainty about whether you're going to get that juxtaposition window. That's our area. We've calculated shale gouge ratio, we've calculated then the fault rock thickness. We just put a table together of the key ones that we're interested in. These are probability of Calaveral touching the quaternary. These are areas. And then what we've calculated here is mean flow per day for an assumed pressure. So what we're assuming here is that we've got a semi-confined aquifer. We've put floodwaters on top of it. Those floodwaters effectively have increased the pressure at the surface. That gives us a delta P to push water into the Calaveral. And it's the time that excess pressure from having the floodwaters, how much does that push us into the Calaveral underneath? And then we can go through and rank each of these by their distributions of flow. So you can get a P10, P50, P90 flow across the day, per day. So how these were used, Phil Hayes, who's now at UQ, was at Jacobs at the time, was doing the modelling. He took these flow units and modified the Blanchetown clay's hydraulic conductivity at where these faults were to go through and say, well, look, here's my distribution of flow I can see across these cells. So, in summary, the things we need. Yeah, we need to use seismic where we've got it, and we need to keep reprocessing the airborne electromagnetics. We're still in the very much in the infancy of AEM. There's a lot more that can be done with this. Seismic now is absolutely fantastic. I would say that in airborne electromagnetics, we're like the 1950s were with seismic, and we have got another 50 years of development of processing that's going to happen. The acquisition will improve gradually, but it's the processing is where we're going to really see the big changes. And that gives us the geometry to look at the faults. It's super important to remember the geology. Hydrogeologists are geologists. They need cross sections. They need to have the geology. It's all about trying to work out the size of that container. In very few hydrogeology reports do I see a proper, well-constrained, non-schematic, measured cross-section. Dick Glenn, who was at the Geologic Survey in New South Wales, produced absolutely beautiful cross-sections in the 1980s and 90s using pencil and paper. These are what are referred to as balanced cross-sections. I've used software here, I've used Lithotech in here to make a balanced cross-section. This is actually forward modeled. But these models are geologically correct and geometrically correct. Now, unless we get the geometry right, we've got no chance of working out where to put your permeabilities and hydraulic conductivities. So getting this geometry right. So we need cross-sections that describe the geology. Aquitards. The fundamental thing defines the aquifer. It's the bucket. It's how big is this thing. As many of you know, I really like to drink coffee, and I drink coffee out of cups like this. And this looks like a beer glass, but it isn't. This is my coffee. If I drank beer out of this, it wouldn't be much fun. And if I drank coffee out of a beer glass, it wouldn't be fun either. The key thing to getting a sense of how our aquitards is to look for flooding surfaces and to use sequence stratigraphy to work out where these fine-grained rocks are deposited. It gives us a time constraint, geologic time constraint, but it gives us a depositional process to say, okay, I've got fine-grained rock that's been distributed everywhere here because I was now under 20 metres of water. So Lake Bungunya is a fantastic case. We know that the Murray River was shut down and it was flooded, and all the Murray River water came out to a massive lake, and all the fine-grained material then was deposited in a consistent layer through the system. And it's important to represent that as thickness maps or isopac maps. Go through and do all the characterization of the hydraulic properties of it, but also work out how thick it is, how thin it is. It's most important how thin it is, and tabulate that and show it really clearly. My Blanchetown clay is somewhere between 8 and 12 meters thick, and it's most likely 10 meters. Simple. Let's see a nice map of it. And we need consistent fault models. These faults have to have demonstrable displacement. If you can show this displacement and you can't measure how much, you might be, there's at least 300 meters displacement. You can start to produce some indicative models, but you need to demonstrate the displacement and show these. And Allen maps aren't needed for all cases, but they're a really good way of working out these areas of juxtaposition, because these areas of juxtaposition are what drives the flow. They're far more important, I think, than the permeability of the fault rock, because as soon as that fault rock tends to zero, it's the area term that wins. And we can measure the area. It's really hard to measure fault rock thickness. Have a look at Sylvia's work, and let alone the fault rock properties. And we've forgotten to do a lot of these things. This is one of the first cross sections recorded. It's recorded by this laird who had 2 coal mines, and he wanted to show that they had mined this contiguous seam across a fault. And so this is from the 1700s. This actually came from William Smith's diaries or papers, and Smith was the fellow who was a surveyor on the canals all through England, and Smith did a fantastic job as they dug the canals, measuring and noting the geology and the geologic changes. Now, this basic geology is incredibly powerful. Up here we've got one of William Smith's cross sections, beautifully drawn cross section across a southern bit of England. Sitting underneath it is a 3D seismic survey, and you can see that there's a strong concordance. He hasn't done all of this, but there's a strong, obviously he hasn't drawn down here, but there's a strong concordance between what the seismic section's showing and what the deep seismic. This guy had it right. It describes the geology really well. And this is stuff it's old-fashioned, can be done with pencil and paper. There's no excuse for it not to be in an environmental impact statement, to be honest. So just thinking about some scenarios for introducing faults into groundwater analysis. So Bill and I had a really good think about this, and fundamentally you can break it out into some end members. Hey, let's go through and show in this area that faults aren't important. I'm doing an environmental impact statement for a development, and I'm going to show you the faults aren't important. And there's quite a few current cases just now where people need to be able to show this, and I don't think are demonstrating it at all adequately. It's actually relatively easy to do. It's a shoe-in, and you don't have to do lots of geometry. Basically, what you need to know is where you've got faults, map out where you've got the displacements, and show that those displacements where you've got faults are significantly less than the regional aquitard thickness. Not that hard. Map my aquitard, produce some end members, high, low, medium case for my aquitard thickness, produce a set of distributions for my aquitard thickness. So here I've got my distribution, I've got my aquitard thickness maybe marked in here. Here are all my faults in here. I can see, where I am. Now, what I'm interested in this area is, well, these are all the faults I've measured in my area, how big would that fault need to be to remotely get a break in the aquitard? And I can use this relationship to sit there and say, well, if my aquitard is 50 meters thick, I need a fault that's 10 kilometers long. So would that fit in the area, or would I not be able to see it? Well, what would stop me seeing? So you can actually use fault statistics and isopachs to really quite elegantly show that faults will not breach your aquitards. So that's one end member. The second one is, I'm in an area where there's no regional aquitards. I'm a stack of aquifers, and I'm trying to do some development, either extraction or pumping into the aquifer, and I need to understand what's happening with my faults. Now, if there are no aquitards, then I don't have the geometry issues. I've just got, I may have some slight differences in my aquifer properties, but the thing that's really different is I've got damage zones with fractures in there. And it's all about defining where my faults are and trying to estimate how wide those damage zones are. So this is the work that Sylvia's work in Miri, and you can see there's my fault slip surface, and she's gone through and said, this is the damage zone on the upthrown footwall side, here's the damage zone in the downthrown side. We can go through and use, start to say, well, look, is there a relationship between thrown and damage zone? And I think Sylvia's work is showing that there is a good relationship, and certainly Sylvia's other supervisor shows really nice. Zoe Shipton shows really nicely that there are some sensible relationships between damage zone width and fault displacement. So if I know what my displacement is, I know how continuous my fault is, I've got some sense of how these systems are going to work. Looking at my displacement profiles, if I've got two faults and they look as though they're together, if I can actually show they're separated and I go relay around, well, I don't have connection from here to here. I'm not going to necessarily see flow all the way along that system. So that is actually really simple to do. Just map out the displacement. You don't need to produce any Allen maps. You still want to produce cross sections, still want to produce maps, but you can actually start to say, well, look, how wide is my damage zone? How much impact is this going to have on my flow modeling? So then my third scenario is the one that's more complicated. This is where I've got one or many aquitards, and so I've got multiple combined, I've got one or many confined aquifers. And I'm sorry, in that case, you're going to have to make fault models. You're going to have to make surfaces. You're going to need to demonstrate how that fault the area of juxtaposition is. You're going to need to look at what flow you've got across these. But I don't know that this is so common. I think many of the groundwater studies where we're inducing faults are more like this one here, where we've just got a fault sitting inside the aquifer. And we know we've got a fault sitting in the aquifer. Well, it's a case of saying, well, how do we increase the flow parallel to the fault? We increase the fault parallel to the fault because we've got fractures. Let's model the fractures. Let's put observation wells in and look at those fractures. So this last case, I think, is far less common, but nonetheless, it's not that hard. You just need to produce fault models and get juxtapositions. So what I've put together, and I'll put this up on our website, and I may end up just doing almost a TikTok fault flow cheat sheet. This is a little cheat sheet that, it's intended to be up as an A3 diagram plotted up on the wall, just as a reminder of what to think about with the faults. Fundamentally, faults are geometric features. They're not permeability features. They're geometric. They need to have demonstrable displacement. And I've put some numbers in here just so you can keep running back, like my accountant does. He said, well, Titus, how come you spent that much money? Surely you've missed something. I forgot to put my petrol down. So what put these numbers down is to allow you to do that sanity check. So the faults are like to be 1 to 10 kilometers long. They're like to have systematic displacement, tens of meters, maybe hundreds. The damage zone is going to be in tens of centimeters. And the fault core is going to be in millimeters. So you can see we're going from kilometers to tens of meters to centimeters to millimeters. We've got this real trickle down effect, and that's why this damage zone idea doesn't really, we come back to, there's my damage zone, sorry Optus, but that's my Telstra, that's my telephone provider, but that's the size of my fault zone. Aquitards, map them back in a sequence stratigraphic framework. They need to be regionally extensive, and they're likely to be tens of kilometers square in area. Probably, depending on the area, 1, 10, 20, 50 meters thick. And it's important to work out how thick they are. Within your aquifers, I don't care what unit you use for doing your general hydrogeology, start to think about using thinking about matrix porosity and storativity. I think it's important to do that because we're talking about these juxtaposition windows, and we've got these strange relationships between one on one side and the other on the other side. So actually thinking about matrix porosity, matrix permeability, and fracture transmissivity and fracture storativity is important, because the cross-fault flow in the matrix, it's all about the juxtaposition area. That's the key term. Whereas with the fractures, it's all about that aperture as the key thing. So try and use that. And remember, with your matrix flow, your fractures are going to be in the order of 1% storativity, but their capacity to move fluids around is phenomenal. We haven't gone through this in a great deal of detail, but fault-flown groundwater is all single phase. We're not dealing with oil and gas. We don't have capillary effects. There's a whole bunch of literature in oil and gas about how you can't move oil into water, and we don't have to worry about that. All single phase. You might have some slight salinity differences, but your viscosity differences are within the confines of the aquifer are going to be fairly similar. There might be the salinity differences may be more important at density rather than viscosity. And what we're going to see in this single phase flow system is that the strike is going to be parallel. So we've got this little diagram in here saying, well, look, I've got myself a fault core. I've got a damage zone with a width. Flow is going to be enhanced parallel to the damage zone. If that's my permeability tensor, my fracture transmissivity is going to be greatly increased, orthogonal. I may have some reduction of flow across it. So I can start to have this little mental model about how flow is going to move around here and the dynamics of it. And if we're in this confined aquifer, semi-confined aquifer, it's all about this area of juxtaposition. Is the area of A versus B that's going to correlate the flow. Finally, just try and remember mechanical stratigraphy. This is the stuff under Canberra. We've got a pile of different mechanical stratigraphy. Gives us an idea about how we're going to get our fractures. So, quote the Spice Girls, tell me what you really, really want. What I want is some nice geometry. Get me some geophysics. Show me some geophysics. Show me how you've derived your geometry. Then present it in a decent cross-section. Representative 1 or 2 cross-sections across the area you're trying to look at. Show me you don't have faults in the cross-section. Show me it's flat and boring. But at least give me a cross-section that understands in scale how thick my aquifers are, how, whatever it is that I'm concerned about, how thick my aquitards are. Characterize your aquitards. Sure, go and do a whole lot of lab experiments and those sorts of things, but let's actually see sequence stratigraphy and mapping of thicknesses of aquitards. It's not hard. Have a depositional model about why the aquitards there. Is it there because of whatever? And describe them as distributions as well as having maps. Maps are easy. We used to use lots of maps. More and more we've got 3-dimensional models, but if you're putting in a report, it needs to be there with the map. Maps, you can count contours. Maps, you can check the displacement. And maps with tick marks. Almost mandatory. The map needs to show the data that was used to make it. It needs to show you where the AM lines are. It needs to show you where the wells or boreholes are. So you understand where the data is and where the interpretation is. With this map, we can then start to get good, decent fault statistics. And if you build up fault statistics within an area, they become useful for other people. They're useful for you for looking at further projects. So those statistics. And then make sensible, good fault models that demonstrate the areas of juxtaposition. It's not that hard. It'll really help you. It gets you a model that demonstrates you actually know about it rather than saying, hey, the faults aren't a problem. I hope this helps. We're putting together training courses to take this in a modular sense so that you can dip in and out of working out what's important and what isn't important. But fundamentally, these are the things. Show us your geophysics, use geophysics. Show us your cross-sections. Characterize your aquitards and thicknesses. Put maps with faults marked on them properly with contours you can tick marks on your contours. Sorry, not faults you can kick. Faults that you can count and have tick marks, and show fault statistics, and when needed, and it's only when needed, start producing these Allen maps, start producing fault models, because you may not remember we've got those different models where, if there's whopping great big aquitard, I just need to show the fault doesn't cross it, or I don't have an aquitard, in which case it's all about the fractures.
Hi, I hope you enjoyed our chat about groundwater and faults. We're putting together a modular training, so if you are interested in faults and hydrogeology, let us know. Next week we're going to be changing tack again. We're going to be looking at some fields on the onshore Otway. These fields are older gas fields that are now being used as part of a laboratory for looking at CO2 sequestration. Hope you get to enjoy those too. Bye.